Hello, this is Richard Hammack's Calculus 1 course. We are in part 2 of the course on limits. Today, lecture 13, limits at infinity. Previously, in lecture 12, we introduced infinite limits, those of the form limit as x approaches c, f of x equals infinity. Today, we switch things around and look at limits like the limit as x approaches infinity of f of x equals a finite number L. To indicate what we mean by this, think of this function f of x. Take a positive value of x and look at the corresponding f of x. We're going to investigate what happens as x gets bigger and bigger and bigger as it moves towards positive infinity. As x gets bigger and bigger and bigger, you'll notice here that f of x is getting closer and closer to the finite value of 2. And the bigger x gets, the closer f of x is to 2. As x moves off to positive infinity, f of x approaches the finite value of 2. And we express this by writing the limit as x approaches infinity, f of x equals 2. In the graph, I've drawn a horizontal dashed blue line. This line is called a horizontal asymptote of f. It's the line y equals 2. It's a horizontal asymptote. Horizontal asymptotes are not technically parts of the graph of f. They're just lines that we draw to help us understand the behavior of f. This horizontal asymptote y equals 2 is drawn in to emphasize the fact that as x goes to infinity, f of x gets closer and closer to 2. The point xf of x on the graph gets closer and closer to that horizontal line as x goes to infinity. It sort of squeezes in on the horizontal asymptote. I want to emphasize that when we say the line y equals 2, we're not talking about a number y equals 2. We're talking about a line y equals 2, the graph of the equation y equals 2. That's the set of all points xy on the plane where y is equal to 2. Those are the points x comma 2 that are at height 2 on the plane. That's just this dashed horizontal line, the horizontal asymptote. If you like, you can think about this as y equals 0 times x plus 2. That's a line with slope 0 and y-intercept 2. Either way, it's important to realize that when we write, as we do here, y equals 2, we're talking about a line and not a number. We're talking about a horizontal asymptote. And sometimes we'll say the horizontal asymptote occurs at y equals 2, but we're talking about a line. Let's also look at what happens if x approaches minus infinity. Take a negative value of x and look at f of x. And now let x get bigger and bigger in the negative direction. Let it approach negative infinity, and look at what happens to f of x. As x approaches negative infinity, f of x is getting closer and closer to negative 3. As x moves off to negative infinity, f of x approaches minus 3. And we write that as the limit as x approaches negative infinity of f of x equals minus 3. This other dashed blue horizontal line is also called a horizontal asymptote of f. The line y equals minus 3 is a horizontal asymptote of the function. As x goes to negative infinity, the corresponding points x, f of x on the graph of f get closer and closer to that line. They squeeze into that horizontal asymptote. And again, by saying the line y equals minus 3, we're talking about the graph of the equation y equals minus 3. It's the set of all points xy on the plane where y is equal to minus 3. That's all of these points at height minus 3 on the plane. And again, you could think about that as y equals 0 times x minus 3, a line of slope 0 and y-intercept minus 3. So to distill from this page some definitions, we say that the limit as x approaches infinity of f of x equals L means x going to positive infinity forces f of x to approach L. Limit as x approaches minus infinity of f of x equals L means x approaching minus infinity forces f of x to get closer and closer to L. So here on this picture, we've illustrated these definitions for L equals 2 in the first case and L equals minus 3 for the second case. Also, in general, if ever you have the limit as x approaches infinity of f of x equals a number L, or the limit as x approaches infinity, negative infinity of f of x equals L, as we do in this picture, then we say the line y equals L is a horizontal asymptote. So you will have at most 2 horizontal asymptotes for any function, one for x approaching infinity and the other for x approaching negative infinity. And of course, many functions don't have any horizontal asymptotes at all. One final thing before we move on. Whenever we have a limit like this one or this one, where x is approaching infinity or minus infinity, and we get an answer L, that's called a limit at infinity. It's as if x is at infinity, moving towards infinity, or minus infinity. And limits at infinity, limits that look like this, are the topics of today's discussion. We say that the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x describe the so-called end behavior of f of x. These limits tell us what's happening at the ends of the number line, positive infinity or negative infinity. To indicate this, think about the graph of y equals e to the x. For this function, if x goes to negative infinity, e to the x is getting closer and closer to 0. So we see that the limit as x approaches negative infinity of e to the x equals 0. Whereas if x goes to positive infinity, e to the x is just getting bigger and bigger and bigger. It's approaching infinity. We might write the limit as x approaches infinity of e to the x equals positive infinity. So these two limits, we say, tell us the end behavior of this particular f of x. As x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x approaches 0. For the graph of y equals tangent inverse of x, as indicated here, remember tangent inverse of x is the portion of the graph tangent of x between negative pi over 2 and pi over 2 reflected across the line y equals x. So the graph looks something like this. The vertical asymptotes of tangent turn into horizontal asymptotes for tangent inverse. And you see here that as x approaches negative infinity, tangent inverse of x is just getting closer and closer to negative pi over 2. We write the limit as x approaches negative infinity of tangent inverse of x equals minus pi over 2. Whereas if x goes to positive infinity, you can see from the graph the tangent inverse of x approaches pi over 2. Limit as x approaches infinity of tangent inverse of x equals pi over 2. So these two limits describe the end behavior of tangent inverse of x. And we get two horizontal asymptotes, y equals pi over 2, and also y equals negative pi over 2. Whereas up here with e to the x, we only had one horizontal asymptote, which was the x-axis. Let's look at the end behavior of sine of x. As x goes to infinity, sine of x doesn't approach any single number. It just oscillates up and down. So we say the limit as x approaches infinity of sine of x does not exist. And the same for x approaching minus infinity. So because we don't get finite values for the infinite limits for sine of x, we say that sine of x doesn't have any horizontal asymptotes. But now think about taking sine of x and multiplying it times 1 over x. And we get a slightly different looking graph. Notice that 1 over x gets smaller and smaller and smaller the bigger x gets. It gets closer and closer to 0. So by multiplying sine of x by this small number for when x is big, you get a graph that looks like this. The y values for sine of x are squelched down closer and closer to 0. The graph still oscillates up and down, but those oscillations become smaller and smaller as x gets bigger. Notice that this function is really, it's sine of x over x, which is a familiar function to us. We saw previously that as x approaches 0, sine of x over x approaches 1, and you see that happening here as x gets closer and closer to 0. Sine of x gets closer and closer to a y value of 1. Now there's a hole in the graph at x equals 0 because you can't plug in 0 to the function, you'd be dividing by 0. But we are here interested in the end behavior of sine of x over x, not those values of x that are close to 0, but the very large values of x. And you can see here that the limit as x approaches infinity of sine x over x equals 0. As x gets bigger and bigger and bigger, although sine of x turns positive and negative, it squeezes in to y equals 0. So the x-axis is a horizontal asymptote. For the same reason, we would have the limit as x goes to negative infinity of sine x over x equals 0. How about the function y equals 1 over x squared plus 1? Let's think about its end behavior. As x goes to infinity, the denominator x squared plus 1 gets bigger and bigger and bigger and bigger, so the reciprocal of that is approaching 0. So the limit as x approaches infinity of 1 over x squared plus 1 equals 0. And again, our x-axis is a horizontal asymptote. For the same reason as x approaches negative infinity, the x squared plus 1 is a positive number getting bigger and bigger and bigger. So its reciprocal is approaching 0. So also in this picture, we have the limit as x approaches negative infinity of 1 over x squared plus 1 equals 0. So in these previous two pictures, we had only one horizontal asymptote because the limits as x went to infinity and minus infinity were both equal to the same number. I'm going to state a few fundamental facts that will be useful for us. First of all, the limit as x approaches infinity of 1 over x to the power of n equals 0 for any integer n. As x gets bigger and bigger and bigger, x to the power of n is also getting really big, so its reciprocal has to get smaller and smaller, it approaches 0. Also, as x approaches negative infinity, 1 over x to the power of n gets closer and closer to 0, because you have the reciprocal of a number that's getting bigger and bigger and bigger. So that reciprocal is getting smaller and smaller. And you can see this for n odd, the graph of y equals 1 over x to the n tends to look like this. As x goes to positive infinity, the function is positive but getting smaller and smaller and smaller. As x goes to minus infinity, the function is negative, but that negative number is getting closer and closer to 0. So we have the limit as x approaches minus infinity of 1 over x to the n equals 0. Whereas if n is even, the graphs tend to look like this. As x goes to either positive infinity or negative infinity, 1 over x to the power of n approaches 0, as you can see from the graph. So these two fundamental facts, they really should hardly bear mentioning. You should already immediately, as soon as you see these two limits, know that the answer is going to be 0. Or maybe you have to sit and look at it for like 2 seconds, and you'll see that the limit equals 0. I'm just stating this for reference because these two fundamental facts, we're going to tend to use them quite often. We're now going to talk about the end behavior of rational functions. So the problem here is going to be to look at the limit as x goes to infinity, or maybe negative infinity, of a rational function f of x over g of x. Meaning that f of x and g of x are just polynomials. A rational function is a quotient of 2 polynomials. These kinds of limits come up often, and on this page, I'll tell you how to deal with them. There's a basic strategy that's always going to work for limits at infinity of rational functions. What you're going to do is find the highest power of x that occurs on the top and the bottom, and you're going to multiply by 1 in the form of 1 over x to that highest power divided by itself. This will always work for a limit at infinity of a rational function. It's going to simplify things so that our limits have these two fundamental limits that we saw on the previous page in them. I'll show you how this works. Look at the limit as x approaches infinity of 5x cubed plus x over 2x cubed plus 7. When we look at this, we see that the highest power of x on the top and the bottom turns out to be an x to the power of 3. You look at the entire rational function, you look for the highest power of x, and it's 3. So we're going to simplify this limit by multiplying by 1 over x cubed divided by itself, like this. Now that doesn't change the limit at all, because we're just multiplying times 1. But then we're going to distribute the fractions into the top and bottom. So if you distribute the 1 over x cubed into the top, 1 over x cubed times 5x cubed is 5, and 1 over x cubed times x is 1 over x squared. Whereas on the bottom, the 1 over x cubed times the 2x cubed becomes a 2, and the 1 over x cubed times the 7 becomes a 7 over x cubed. Now if you look at these limits, or the limit here, x is going to infinity, so we know that 1 over x squared is approaching 0. And likewise, 7 over x cubed is approaching 0 as well. We're using those two fundamental facts that we had on the previous page. So this limit is 5 plus 0 divided by 2 plus 0, because these fractions both turn into zeros. And we get an answer of 5 halves. So here, for this function, the line y equals 5/2 would be a horizontal asymptote. But the point is, we were able to evaluate this limit of as x goes to infinity of a rational function by this trick, multiplying by 1 in this form. Let's try another one. Almost the same function, almost the same limit. The limit is x goes to infinity of 5x squared plus x over 2x cubed plus 7. The only difference is I've changed this x cubed on the top to an x squared. Well, when you look at this, your highest power of x is still 3. So again, you'd multiply this whole limit by 1 over x cubed divided by 1 over x cubed, just as you did before. And then you multiply n. Distribute n. The 1 over x cubed times the 5x squared is a 5 over x. And then it times the x is a 1 over x squared. Whereas on the bottom, we're going to get the same thing that we got in the previous line. We get 2 plus 7 over x cubed. And now as x goes to infinity, the 5 over x and the 1 over x squared and the 7 over x cubed, those shrink to 0. Those reciprocals disappear. They turn into 0. And we get 0 plus 0 divided by 2 plus 0. And that's just 0. For another example, look at this one. It's almost the same as what we had previously, but this time I've got the highest power of x on the numerator rather than the denominator. Applying our strategy would tell us to multiply by the reciprocal of the highest power of x, which is x cubed, as we did before. And now multiply through. On top, 1 over x cubed times 5x cubed is 5, and 1 over x cubed times x is 1 over x squared. On the denominator, the 1 over x cubed times the 2x squared is a 2 over x, and the 1 over x cubed times the 7 is a 7 over x cubed. What's happening here? Well, these reciprocal terms that you see in these three places, they're all approaching 0. So the top is approaching 5 plus 0, but the bottom is approaching 0 plus 0, or 0. This is a situation where we're getting an infinite limit. The top is approaching 5, but the bottom is approaching 0. And moreover, x is going to positive infinity, so this 2 over x and the 7 over x cubed, they're both positive. So the bottom is approaching 0, and it's a positive number. So the quotient in this limit, you've got the top approaching a finite number 5, the bottom approaching 0, and it's positive. We're going to get positive infinity for this limit. So the limit as x approaches infinity of this rational function equals positive infinity. Let's do the same problem, but this time let x approach negative infinity of 5x cubed plus x over 2x squared plus 7. Again, we multiply through as we did before, and it works out just as we had on the previous line, except x is approaching minus infinity. So this numerator, 5 plus 1 over x squared, it's approaching 5 because 1 over x squared goes to 0. And on the denominator, again, we're approaching 0, but look what's happening here. X is approaching minus infinity, so x is negative. So 2 over x is a very small negative number, and 7 over x cubed is a very small negative number, and their sum is negative. So the denominator is approaching 0, and it's negative. So on top we have a positive value. The numerator is approaching positive 5. On bottom, the denominator is approaching 0, and it's negative. So we have a positive divided by a very, very small negative number. So this answer is going to be negative infinity. So you can always apply this strategy of multiplying by 1 in this form whenever you're working out a limit of a rational function, a polynomial divided by a polynomial. And it's very important to note that this strategy that we've mapped out, it's only for infinite limits, where x is approaching infinity. If you had a regular limit like x is approaching 3 or something like that, you would not use this strategy. This only works for x approaching infinity or minus infinity, because the thing that made it work is the 1 over x squared, or the reciprocals of these high powers, they were turning into 0. That's what gave us our answer. And to get those to turn into 0, x has to be approaching infinity or minus infinity. So you should work lots of exercises of this form until you feel really confident in your work. And as you work these infinite limits of rational functions, or limits at infinity of rational functions, you'll start to see some shortcuts. You can base your answer on the highest powers on the top and the bottom. And I'll show you what I mean by that. I should say here that you can always work these problems in the way we did on the previous slide. But after a while, you'll start to see patterns like this. You've got the limit as x approaches infinity of 5x cubed plus x squared minus x over 7x minus 8x cubed. No matter how you do it, you know to look at the highest power of x that you see. And it's x cubed, the 5x cubed, and the minus 8x cubed here. And I'll highlight those in blue. If you multiply by 1 over x squared divided by 1 over x squared, you're going to get a situation where all these lower powers of x, they tend to disappear, and the 5x cubed turns into a 5, and the negative 8x cubed turns into an 8. And so you're going to get an answer of just 5 over minus 8, or negative 5/8. So after you've done these limits at infinity of rational functions a few times, you'll start to pick up on this shortcut. Look for the highest powers of x on the top and bottom. If they match, then just collect those coefficients and form a fraction from them, and that's going to be your answer. I would recommend that you don't do this trick until you've worked a few of these, and so you see a few steps ahead, and so you're doing this shortcut organically. You're just basically skipping steps, not applying some rule. For another example, look at the limit as x goes to infinity of 5x cubed plus x squared minus x over 7x minus 8x to the fifth. So here, your highest power of x, it only occurs at the top. I beg your pardon. The highest power of x is x to the fifth. It only occurs at the bottom, the minus 8x to the power of 5. There's no x to the power of 5 on the top. Now, what's going to happen here, if you think about it, by your strategy from the previous page, you'd multiply by 1 over x to the fifth divided by 1 over x to the fifth. You'd get a bunch of fractions here with the power of x on the denominator at the top, and they'd all turn into 0, and the 7x would turn into a 7 over x to the fourth. That would approach 0 as x goes to infinity. But the minus 8 over x to the fifth would turn into a minus 8. So we'd be getting in the limit 0 divided by 8, and that's 0. You're always going to get 0 if your highest power is only on the bottom, as in this case. And again, when you're first working these, if this is new to you, apply the strategy from the previous page, multiply by 1 over x to the fifth divided by itself, and work it through. Only after you get to the point where you've done enough of these will you see this shortcut and how it works. So work your way up to it if you're not there already. Also, imagine you had the highest power of x, this time on the top, not the bottom. The highest power here is x to the fourth. So if we multiplied by 1 over x to the fourth divided by itself, then you'd have a 5 at the top, and then some reciprocals of powers of x here and here. And on the bottom, you'd have reciprocals of powers of x. The numerator would approach 5, and the denominator would shrink to 0. And so we'd get infinity. And if you think about what's happening there, on the bottom, the 7x minus 8x cubed, this 8x cubed is much bigger than the 7x as x goes to infinity. So we're going to get a negative on the bottom. So it's a positive divided by a negative. We get a negative infinity. So you'll notice this as you work these. Whenever you have the highest power of x on the top, you're either going to get positive or negative infinity. If you feel comfortable with this shortcut, by all means do it. Otherwise, just multiply by 1 over x to the fourth divided by 1 over x to the fourth. Carry it through as on the previous page. You'll see that you get negative infinity. You will tend to get, or you will get, plus or minus infinity if ever the highest power is on the top. Same problem if x were approaching negative infinity here. X is a negative number, so this negative 8x cubed would dominate the bottom. It would be negative of a negative number cubed. That's positive. So you're getting positive divided by positive. And it's positive infinity in this case. So whenever the highest power is on the top, you're going to get plus or minus infinity. Apply the shortcut if it works for you. If not, if you're not sure whether you're going to get positive infinity or minus infinity, just go back and do it the previous way. For the next example, let's examine the end behavior of the function f of x equals the square root of 7x squared plus 4 divided by x minus 3. This is not a rational function because on the top you have a square root function, the square root of a polynomial. So we've got to be kind of careful. We wouldn't want to apply our shortcuts because they only work for rational functions. What are we going to do here? Before we get started, I want to put an algebraic fact off to the side that we're going to use. Remember that if a is a positive number, or at least if a is not negative, then a times the square root of b is the square root of a squared times b. You can bring the a inside as an a squared. Working backwards, the a squared can come outside as an a. This only works if a is positive. It fails if a is negative, because notice that if a were negative 2, minus 2 times the square root of b, that does not equal to minus 2 squared times b in square root. The reason is this side is negative, but the side over here is positive. The takeaway is that we can use this algebraic fact, and we will use it in just a moment, whenever a is positive. It comes inside of a radical as an a squared. You can't do that when a is negative, as indicated here. So let's jump back to this problem. What are we going to do? We want to examine the end behavior of this, so we're looking at the limit as x goes to infinity or minus infinity. Let's try the limit as x goes to infinity of this function first. We could try this trick of multiplying by the highest power of x divided by itself. It can't hurt. We're just multiplying by 1. But what's the highest power of x? We have an x to the power of 1 here. But here we have an x squared, but that's inside of a square root. So for all intents and purposes, you're talking about the square root of x squared, and that's just x. So you would surmise here that, so to speak, the highest power of x is just x to the power of 1. So we would multiply by 1 over x divided by itself. Now that hasn't changed anything because we're just multiplying by 1. Here x is going to infinity, so 1 over x is a positive number, has a positive value. It might be pretty small, but it's positive. So because it's positive, that 1 over x, it's allowed to come into the radical as a 1 over x squared, as we did here. So let's try that. On top, the 1 over x, we're bringing it inside the radical as its square. We're applying this algebraic rule. On the denominator, the 1 over x multiplies by the 3 to give you a 3 over x and times the negative x to give you a 1, or negative 1. So on the bottom, we get 3 over x minus 1. Now let's distribute the 1 over x squared into the parentheses. This is 1 over x squared. Multiply it through, and you get, let's see, the 1 over x squared times the 7x squared is a 7. The 1 over x squared times the 4 is a 4 over x squared. So we have the limit as x goes to infinity of this expression now. And as x goes to infinity, the 4 over x squared and the 3 over x turn into 0. So you get the square root of 7 plus 0 divided by 0 minus 1. And that's minus the square root of 7. So we've successfully evaluated this limit at infinity. Let's look at the limit as x approaches negative infinity of the same function. So again, we would say that the highest power of x is x to the power of 1. So we could multiply by 1 over x divided by itself, which is perfectly fine. That's equal to 1. So that doesn't change anything. But watch out here. In our next step, we're going to want to bring that in as a 1 over x squared, as we did here. But look, x is approaching negative infinity in this limit. It's a negative number, so 1 over x is going to be a negative number. We can't bring a negative number inside the radical as its square. That just doesn't work. How can we fix that? Easy. Instead of multiplying by 1 over x divided by 1 over x, multiply by negative 1 over x divided by negative 1 over x. That's equal to 1, and because x is a negative number and 1 over x is therefore negative, the negative of that is going to be positive. So here we're multiplying by a positive number, negative 1 over x, divided by itself. So because negative 1 over x is positive for negative values of x, we're free to multiply, to bring this positive number inside a radical as its square. So then, working just as we did before, the negative 1 over x comes inside the radical as a negative 1 over x quantity squared. On the bottom, it multiplies through, it distributes in, and gives us a negative 3 over x plus a 1. The negative 1 over x times the negative x is 1. Simplifying, on the top we get, let's see, it's the limit as x goes to infinity of square root of 7 plus 4 over x squared. When we distribute this in, on the bottom we still have minus 3 over x plus 1. And again, as x goes to, and I'm sorry, it's a typo, this should be x goes to negative infinity, as it was over here. As x goes to negative infinity, the 4 over x squared and the negative 3 over x, they turn into 0. And we get the square root of 7 plus 0 divided by 0 plus 1. And that's positive square root of 7. So the limit as x goes to negative infinity of our f of x is positive square root of 7. So here we're picking up two horizontal asymptotes, y equals minus square root of 7 for the first infinite limit, and y equals the square root of 7 for the second one. If you graph this function, it's going to look something like this. I took a graphing utility, I graphed our function f of x, and notice that as x goes to positive infinity, f of x is getting closer and closer to this horizontal line, which would be at negative square root of 7. As x goes to negative infinity, f of x gets closer and closer to this above dotted line, which would be the horizontal asymptote right here at y equals positive square root of 7. And notice that you have a vertical asymptote at a certain x value right here. That, where would that be? That would be at x equals 3, where the denominator turns into 0, and the numerator is non-zero. So you get a vertical asymptote right there at x equals 3. Okay, you should work enough examples or enough exercises from the text to the point where you feel comfortable working out limits of this form. It's important when you're doing these to recognize which technique to apply. I emphasize that the techniques we've talked about today are only for infinite limits. The limit as x approaches infinity. If you have a different kind of limit, you might have to use a different technique. And I'll illustrate that on this page. Suppose we had the limit as x approaches infinity of x squared plus 4x plus 3 over x squared minus x minus 2. Well, you'll recognize this as a limit at infinity of a polynomial. You know now to pick off the highest power of x, which is x squared. It happens on the top and the bottom. So you can see that the answer here you can get from applying our strategy, multiplying by 1 over the highest power divided by itself, multiplying through on the top and the bottom to get this. And now as x goes to infinity, all of these reciprocals of powers of x, they turn into 0, and you're left with 1 plus 0 divided by 1 minus 0, which is just 1. This technique of multiplying by the reciprocal of the highest power of x divided by itself only works when x is approaching infinity or minus infinity. And you should recognize that. On the other hand, what if you had almost the same problem, the same function, but instead of x going to infinity, x is approaching 1. The limit as x approaches 1 of x squared plus 4x plus 3 over x squared minus x minus 2. Well, here we can look at this, and x is approaching a finite number, and you see that the denominator, it's approaching 1 squared minus 1 minus 2. That's not equal to 0. So here we can just apply a limit law. In fact, we have the limit as x approaches 1 of a rational function. We know that to get the answer, you can just plug in 1 wherever you see an x. And you get an answer of minus 4. So for this limit, of course, we used an entirely different technique than the one above. They're different kinds of limits, and they call for different techniques. What about the limit as x approaches minus 1 of x squared plus 4x plus 3 over x squared minus x minus 2? In this case, the denominator is approaching minus 1 squared minus minus 1 minus 2, and that's 0. The denominator is approaching 0, and also if you plug in negative 1 to the numerator, it's 0 too. So we're getting 0 divided by 0. So we know to apply the technique where we factor and try to knock out the term that's turning into 0. Here as x is approaching minus 1, when we factor the denominator, you can see that the x plus 1 is the problematic factor in there. It's turning into 0 as x approaches minus 1. So you're hoping to cancel that x plus 1. And in fact, when you factor the top, you get x plus 1 times x plus 3. The x plus 1s cancel. You get the limit as x approaches minus 1 of x plus 3 divided by x minus 2. And now it's a limit. In fact, it's kind of like the one we had before where the denominator is not turning into 0. You can just plug in the minus 1. And you get an answer of minus 2/3. So in these three limits, they're all involving the same function, but x is approaching a different number or a different entity. And we had to use different techniques. One more example, the same function, but this time let's let x approach 2, and let's say 2 from the right. Working as we did before, we get the same cancellation. We're looking at the limit as x approaches 2 from the right, and here the denominator is approaching 0, but the numerator is approaching 2 plus 3, or 5. We get a situation where the numerator is approaching 5, the denominator is approaching 0, and x is approaching 2 from the right, so x minus 2 is positive. So here we're getting positive infinity. So on these 4 different problems on this page, we had to apply 4 different techniques to evaluate the limit. So as you're studying this material, be careful to recognize which techniques apply to which situations and use the appropriate technique. It's especially important when you're getting ready for your first test, when you're not being quizzed or doing homework problems on a particular section where you're funneled into using a particular technique. Be ready to look at each problem on its own merits and decide which technique to use. To summarize all of this, I have a picture of the graph of this function that is in all of these limits, and it looks something like this if you graph it with a graphing utility. And you can see, sure enough, as x goes to 2 from the right, f of x is going to infinity. The limit as x goes to infinity of f of x is 1, so that's your horizontal asymptote. It's also a horizontal asymptote for x going to negative infinity. And also notice that in this function, when x is negative 1, you get a 0 in the denominator. So you're going to pick up a hole in the graph right there at x equals minus 1. But the limit as x approaches minus 1 is defined, it was negative 2/3. So this hole is at a y-coordinate of negative 2/3. We'll conclude with a couple of other examples. Think about the limit as x goes to infinity of ln of x squared plus 4x over 3x squared minus 2. Looks kind of like the limit as x goes to infinity of a rational function, except you have this ln with a rational function plugged into it. Since ln is a continuous function, we can move this limit into the function, and we get ln of the limit as x goes to infinity of x squared plus 4 over 3x squared minus 2. So inside of ln, we now have an infinite limit of a rational function. And you can see what that limit equals by looking at the highest powers of x. You got an x squared on the top and the bottom. So we know to, using a shortcut, collect our coefficients of 1 and 3 of those highest powers, and this limit is going to work out to 1/3. That limit is plugged into ln, so to get our answer, we have ln of 1/3. Here's another example, and you'll see some exercises kind of like this in your textbook, most likely. The limit as x goes to infinity of the square root of x plus 4 minus the square root of x plus 1. So what is this expression, this function, this difference approaching as x goes to infinity? One strategy that you might want to think about is to convert this to a fraction so that you can analyze it in terms of the thought processes that we've used today. You might strike upon this idea. Multiply the limit by 1 in the form of the conjugate of this expression. Now that's harmless, that's perfectly harmless. You're just multiplying by 1, so you're not changing anything. The question is whether this gets us anywhere. Let's distribute the top into the parentheses here. The square root of x times the square root of x plus 4 times the square root of x plus 4 is x plus 4. Then you have a square root of x plus 4 minus the square root of x times minus the square root of x plus 1. But then you have a square root of x plus 1 times the square root of x plus 4. And then those two cross terms cancel out. And finally, you have a square root of x plus 1 times the square root of x plus 1. And that's minus x plus 1. Bringing the denominator down over, this turns into the limit as x goes to infinity of this difference divided by this denominator. And you'll notice a nice thing happens here. The x's cancel out, and on the numerator you just get a 3. So we have the limit as x goes to infinity of this quotient. And notice we have a finite value of 3 on top. But the square root of x plus 4 and the square root of x plus 1, they're getting bigger and bigger and bigger as x goes to infinity. So this quotient is approaching 0. So our answer to this limit is 0. So you should read your text, work some exercises so you get comfortable with this, and you begin to recognize different strategies and approaches that you might apply, such as in the problems on this page. That's it for part 2 of the course. At this point, after you've worked lots of exercises, you've really got a good grip on limits. And remember, our whole purpose in studying limits was to get at slopes of tangent lines. And that's coming up next in part 3 of the course, where we discuss and define a major part of calculus, the idea of a derivative. I'll see you there. Goodbye.